Greetings and welcome to the Chemistry 222 lecture for Chapter 11, where we're going to look in greater detail at solutions. And we've just went through some chapters where we studied gases. We then looked at some chapters when we looked at liquids and solids and how to have a transition from one to the other. But now we're going to look at probably what is the most useful of all the phases, and that's a solution, at least for chemists. And in a solution, you have two components, the solute and the solvent. The solute is usually the little bit more exciting part, but the solvent, of course, is important as well. So without further ado, let's check out this chapter in greater detail.
When a raw egg is placed in dilute acetic acid, the acid dissolves the shell, but the egg's membrane remains intact. When it is placed in pure water, the egg swells. In a concentrated aqueous solution of corn syrup, it shrivels.
So this is kind of an unusual experiment, but on the left-hand side in that beaker, it shows an egg being placed in a solution of acetic acid. And acetic acid, a weak acid, actually dissolves the shell of the egg. And when the shell is gone, then you have what kind of looks like the middle beaker. You have just the membrane, but the shell is gone. And then what's really interesting is that in the middle beaker, they added water to the egg membrane, and you can see that it got like pretty big. And the right hand side beaker, they, instead of adding water to the membrane, they actually added corn syrup, and corn syrup actually made the membrane shrink. And all of this behavior, like water making the membrane bigger and corn syrup making the membrane smaller, all of this can be explained by the understanding of solutions. Solutions have special properties that exist only when you have a solute and a solvent together. And that's what we're going to look at in this section. So let's get into this stuff and figure out exactly what solutions are all about. So first, some definitions, and some of these we've been over, but some of them I want to go over again just to make sure we're all up to speed. A solution is homogeneous, and if you say homogeneous, it's okay, but homogeneous, it's a homogeneous mixture if you have two or more substances in a single phase. So a single phase would be liquid, solid, or gas, and what's by all means most common for this chapter is the single phase would be like a liquid phase. So the solutions, you'll take like something solid and place it in something like water. You mix everything up and everything is just a single phase. You don't see like little pieces of solid running through the liquid. There are three types of homogeneous mixtures which are really important to chemists. And those three types are called solutions, colloids, and suspensions. And solutions are by far the most important. We're going to talk about all three, but we're going to focus mainly on the solution because solutions are very, very common, and they can do a lot of neat things in chemistry. A solution, also like a colloid and a suspension, solutions have at least two constituents, two pieces that make them up. These two constituents are called solvent and solute, all right? And one part is usually called the solvent, and the other part is called the solute. So here, recognize these names. Solution equals solute plus solvent. You have to have both. Now, they all begin with SOL, and SOL stands for something else, which has some kind of bad words in it, so I don't want to say it on video, but anyway, just realize you have to know which SOL you're dealing with. All right, are you dealing with the whole solution? Are you talking about just the solute? Are you talking about just the solvent? And again, we're going to look primarily at solutions where water is the solvent and some kind of usually ionic compound will be the solute. But in that table down there, you can see there's a whole bunch of different examples of how things can combine in different ways. You can have solid solutions where solids mix with solids like the silver and gold. You can also have gas solutions where two types of gases are mixed together. And the air we're breathing right now is technically a solution of gas. You have different kinds of solutes in different kinds of solvent. I would argue that nitrogen gas, which is the main component of the air we breathe, would be the solvent. And oxygen, the important part to us, would be the solute, but it could be interpreted in different ways.
When nickel chloride is added to water, it dissolves readily. Because more nickel chloride could be dissolved in this solution, the solution is called unsaturated.
Some additional terms that will be helpful in this section are unsaturated and saturated. And an unsaturated solution is usually the kind of solution which is most helpful to chemists. And in an unsaturated solution, you can think about it as the solvent has the ability to dissolve more solute if you were to add it. So in that example, in that video, they added nickel 2 chloride, NiCl2, to water. And they added it in, it all mixed up, there's no more solid left, so probably that's an unsaturated solution. We could add more solid nickel 2 chloride and it would continue to dissolve. But there would finally be a point where as we added nickel 2 chloride, it would stay as solid. It would no longer dissolve. And you probably guessed it, that's when you reach the point of saturation.
When solutions of lead nitrate and potassium iodide are mixed, solid lead iodide precipitates from solution. The liquid remaining in the test tube is a saturated solution of lead iodide. Whenever a precipitation reaction occurs, the solution surrounding the precipitate is saturated with the product of the reaction.
A saturated solution just means that the solvent can no longer dissolve any more solute. And if you see a precipitate, as in a precipitation reaction, you have gotten to the point of saturation. Now, water is a really good solvent, but there are some compounds like lead 2 iodide in the video there, the yellow stuff. It just can't handle that much PbI2. It saturates really easy and it becomes a solid. On the other hand, in the previous video with the green nickel 2 chloride, water can handle quite a bit of nickel 2 chloride. It'll dissolve before you reach the point of saturation where a solid appears. So if you see a precipitate form, that means you've passed the saturation point and solids begin to appear. On the other hand, unsaturated just means you can add more solute and it will in theory still dissolve.
When supersaturated sodium acetate is poured onto a few grains of solid sodium acetate, the amount of sodium acetate dissolved in excess of the saturation point precipitates, forming a solid. Some of the liquid solution, which is now simply saturated, becomes trapped within the solid.
There's also what they call a supersaturated solution, and supersaturation isn't as common, but I did want to throw it in here. Supersaturation, how they usually do this is they'll take some kind of solute, and in this case it was a sodium acetate, I believe, and they place it in water, but they heat the water up to maybe like boiling or 50 degrees Celsius or something like that. And generally speaking, as temperature goes up, you're able to include more solute before it gets precipitated. So they have this hot solution with a lot of sodium acetate in it, and they very slowly cool it down. So it looks just like water. However, if you disturb it, all right, and what they did in the video is they had a seed crystal of sodium acetate, and that disturbed it, so the precipitate started coming out. In the lower picture, you can see how there probably was like a scratch on the beaker, or maybe they bumped it, and actually you'll begin to see solid form right away that way. But anyway, if you have some kind of a disturbance, then wow, precipitation just starts going crazy. It just like pops out of thin air. This is the supersaturation process, and there are some kind of neat uses for it. For us, though, it's just more entertaining. I think that's kind of cool how they can build that little structure of sodium acetate, but you know, I am a chemist. Other definitions which are important include miscible and immiscible, as well as solubility. So miscible just means that two or more, usually liquids, mix together well. They're soluble, all right? If you have something which is immiscible, that means they don't mix well and they'll separate. So as an example of that, if you're 21 and over, 19 in Canada, you can add ethanol, which is basically drinking alcohol, to water, and you can make a mixed drink essentially. That would be two miscible solutes, two miscible liquids coming together. On the other hand, if you try to take something like oil and place it in water, they don't mix very well at all. So oil and water you would consider are to be immiscible. Solubility is another term. Solubility is literally a number that's associated with how much solute can dissolve in a solvent at a specific temperature. So it's usually referenced in grams, sometimes moles, and the graph down there shows the solubility of several compounds. Right about 40 grams per 100 milliliters on the y-axis, there's a kind of a yellowish line for sodium chloride, and you can see it just goes straight across. It is getting a little bit bigger, so that means is that as the temperature, the x-axis increases, the solubility of sodium chloride increases as well. And most of the compounds on there increase their solubility as temperature goes up. So you can see as you go left to right along that graph, most of the lines are getting bigger. Like glucose goes crazy, the sodium acetate goes crazy. However, on the bottom is a compound called cerium sulfate, and cerium sulfate solubility decreases with increasing temperature. So most of these will increase their solubility with greater temperature, but there are some compounds like that cerium sulfate thing that actually decrease their solubility with temperature. We'll talk more about why that's the case in Chem 223. There are some factors that affect solubility, like why some things are miscible and why some things are immiscible. And chemists like to use the idea a lot that like dissolves like. And what that refers to is that as the intermolecular forces of the two things you're mixing get closer to each other, the more likely they're going to mix. So earlier I used the idea of water and ethanol drinking alcohol. They mix really well. They both have hydrogen bonds. They're both very kind of similar on a structural level, no problem. On the other hand, oil and water don't get along very well. Oil is generally nonpolar, and nonpolar things don't get along very well with superpolar things like water that even has hydrogen bonds. On the other hand, if you mixed oil with, say, pentane, those are both essentially nonpolar substances. Those would probably mix pretty well. In the little graph there down below, we have a series of alcohols. So the first one is methanol, like we saw in the OChem chapter. Ethanol, the drinking alcohol, is next, followed by propanol, etc., etc. And what's interesting are the two columns. So the first column shows the solubility in water and the OH group on the alcohol. They get along pretty well. But as you can see, the solubility is going down. Like by the time you get to butanol, it's not infinite, all right, a little bit less, although still pretty good. Pentanol less, and hexanol is the least of all. On the other hand, C6H14, which is hexane, methanol doesn't dissolve very well at all. But you can see the other alcohols dissolve pretty well. Hexane is nonpolar, all right? It's considered more nonpolar than anything. As the alkyl group gets larger, it becomes more like C6H14. It becomes more like a nonpolar substance. So as the alcohols get bigger, they actually are better dissolved in nonpolar solvents like hexane than they are in water, which is kind of an interesting thing to think about. This is a joke I couldn't resist. You can see the poor polar bear. Polar bear goes, "Help, help, I'm dissolving." And the brown bear goes, "But bears are insoluble." Bears like swim in the ocean and lakes and stuff like that. But then poor polar bear goes, "That's easy for you to say, you're not polar." So polar bears would dissolve in polar water, all right? Duh. Anyway, I know I need to get a life, but I couldn't resist. Like dissolves like is the kind of thing to think about. And if you have to guess, like dissolve like is what you want to do. So here's some examples of combinations. So water and acetone get along pretty well. Water is polar, acetone is polar, so probably that's a pretty good mix. The second example, benzene, which is C6H6, it's the circle of carbon compounds, dissolves in toluene, which is methylbenzene. Those two are both both pretty similar. They're basically nonpolar, so they would have induced dipole intermolecular forces. But if you try to mix benzene, which is very nonpolar, induced dipole intermolecular force, that wouldn't dissolve very well in water because water's intermolecular forces are quite different than benzene. Water, again, is polar with hydrogen bonds. They probably wouldn't get along real well. We're going to talk more about solubility in Chemistry 223. We'll talk about some of these phenomena, but with these kind of terms under your belt, we can now get into the idea more about what's happening with solutions. Here's a question you might say. Which of the following solvents would you expect lithium chloride to be highly soluble? So if you put lithium chloride in each of those, which one would it most likely dissolve? Now, if you remember the list of intermolecular forces, the strongest intermolecular force was the ion-ion/metallic force. And lithium chloride has positives and negatives, so that's going to be the ion-ion force. And we want to try and find the compound in the list which is going to be closest in intermolecular force strength to ion-ion/metallic. And you can probably see from that list that one of the options is water. And water, as we talked about, is not just dipole, it's hydrogen bonded. And that is by far the closest molecule in intermolecular force strength to the ion-ion. Lithium chloride dissolves very well in water. That's the ion dipole force that we talked about. If you look at the other compounds, all right, CCl4, CS2, the next one is butane, answer D, and E is benzene. All of those are basically non-polar. They would have induced dipole force. And that's as far away from ion-ion force as you can get. Like induced dipole is the weakest. Ion-ion/metallic is the strongest. So you wouldn't expect any of those to probably dissolve lithium chloride. You would need something with as close to the ion force as you can, and water with its hydrogen bonds definitely closest. Henry's law is a way to talk about the solubility of a gas in a liquid. And Henry's law is really useful for companies that make soda pops, beers, and stuff like that. And the solubility of the gas is represented by that Sg right there. And that Sg, the S stands for solubility of the gas, and it's measured in molarity, all right, big M. And the solubility of the gas equals K, which is called a Henry's law constant. And the Henry's law constant depends on the solvent. So water has its own K value. If you had ethanol, it would have a different K value. But then P is the interesting. P is the partial pressure of the gas above the liquid. And as the pressure of the gas over the liquid goes up, the solubility goes up. On the other hand, if the partial pressure of the gas decreases, the solubility decreases. If you open a can of pop, all right, you're taking a high pressure can of pop. The inside is pretty high pressure, and you're essentially just lowering the pressure down by opening up to the outside. So as the pressure is lowered, the solubility of the gas is lowered, and the gas starts to escape from the liquid. So you have that very satisfying sound effects not necessary, no, but that sound that happens when you open the can of pop that people then think, oh yeah, this must be fresh. All right, well, really it's just Henry's law. You're lowering the partial pressure of the gas, and so the solubility of the gas goes down and the gas escapes, making that cool sound. This is an example of a K constant. This is for oxygen. Oxygen and stuff dissolved in water has that 1.66 times 10 to the minus 6 molar per millimeter of mercury. So you can actually use this. If you multiply it by the partial pressure of the oxygen in there, you can find the solubility of the gas.
When a can of soft drink is opened, a whooshing sound is heard, and the solution begins to release bubbles. The escaping gas is carbon dioxide. Henry's law explains why the gas leaves the liquid only after the can is opened.
In the can, you have a high pressure, like you don't want to shake it up and stuff like that, or else it goes crazy when you open it up. So you have a high pressure, so you have a high solubility. You get a lot of carbon dioxide in the Diet Coke in this case. But then you pop the top and you even pour it into a glass. Now the partial pressure has gone way down. You're going from a high pressure can to a regular 1 atmosphere room environment. And as the pressure goes down, the solubility goes down. So all of this gas, which was dissolved in the Diet Coke or whatever, starts escaping. And you can see that kind of hissing kind of sound that comes out and stuff like that. The industries love that because usually it makes people think that it's refreshing and stuff like that. But you now know it's just all about Henry's Law. Woohoo! Here's a question. After a can of Diet Coke is removed from the refrigerator, opened and left to stand a while, which of the following best describes the changes that cause the soda to go flat, lose its CO2? All right. So the first one, lowering the CO2 pressure over the solution and raising the temperature. Well, yeah, that makes sense. Lowering the CO2 pressure over the solution. Possibly. Lowering the temperature, increase in salt content. Well, definitely answer D is flat out because there is no salt being answered, all right? You're not really lowering the temperature either because it was in the refrigerator. So if anything, you're increasing the temperature, all right? So the options here are lowering the CO2 pressure over the solution and raising the temperature. Or you can think about it as just lowering the CO2 pressure over the solution. Because it's warming up, the temperature is going up, so the CO2 has more action. And of course, you're definitely lowering the pressure by opening the can. So I would argue that answer A is the best. You're not just lowering the CO2, which is really what Henry's Law is all about. And you're lowering it because you're opening the can, the new pressure is less, so the solubility goes out, but you're also raising the temperature, and that has to be part of it. As you increase the temperature, you'll have more of the gas escape and stuff. We saw this back in the gas law. I think answer A is probably the best. C, once again, is not right because you're not lowering the temperature, you're raising the temperature by letting it sit at room temperature. And finally, there's nothing to do with salt, so that would be just a silly answer. Generally speaking, the solubility of solid solutes in liquid solvents will be increasing. And we saw this picture earlier. And again, most compounds, the solubility goes up as the temperature goes up. And that's a generally good rule of thumb. There are exceptions, though. We saw that cerium sulfate thing down below. That would be an example of a compound that actually decreases its solubility with increasing temperature. For gases, on the other hand, though, usually it's the opposite. Raising the temperature lowers the solubility. So back to that Diet Coke example that we left sitting in room temperature, we basically were raising the temperature on it. And the solubility actually decreases with increasing temperature. As the gas molecules have more energy, they're more likely to escape and stuff like that. Warm lakes have less dissolved oxygen than cool lakes, all right? Because the warmth tends to make the oxygen get out of the water. So this leads us into the true properties of a true solution, where you have a true solute and solvent. And the properties of solutions that are only available to you if you have a solution are called colligative properties. So colligative properties are literally properties only exhibited in a solution. If you have pure solvent like water or pure solute, nickel 2 chloride, whatever, you're not going to see any of these. But if you have a solution, oh wow, now you've got some weird things. There are 4 colligative properties. The first one is you end up having a decreased vapor pressure. So vapor pressure goes down. Sometimes it's called vapor pressure depression. Your melting point goes down as well. So melting points will go down, but boiling points will go up. Boiling points actually increase. And finally, the 4th colligative property, osmosis. Osmosis is a type type of a force that happens with solutions, and we'll talk about that in a little bit. Osmosis is the same as osmotic pressure. So if you've heard either one of those terms, we're going to be looking at them both in this section. Colligative properties are something that, again, exists only in solutions. And in a solution, to figure out the strength of these colligative properties, we need to know the number of solute particles relative to the solvent particles. And this is really wild. We don't need to know what kind of solute particles we have. We just need to know the number of solute particles relative to solvent particles. And unfortunately, the concentration unit we've used so much in Chem 221, and will continue to use, by the way, molarity, doesn't really do a good job. All right, molarity is about moles of solute per liter of solution. And what we want to have is we want to know somehow the relative number of solute particles relative to solvent particles. So molarity isn't going to cut it. We're going to talk about some new concentration units here in a little bit, and we will talk about how you can relate them back to molarity, because molarity definitely dominates the chemistry world. 3 new concentration units will be very helpful to us in the upcoming sections. And the first one of these new concentration units is called a mole fraction. So let's say you have a mixture of A, B, and C together, and you wish to describe the mole fraction. Well, the mole fraction of A, let's assume we're looking at A, is going to equal the moles of A divided by the total moles. So you're going to have so many moles of A, B, and C. Mole fraction of A would be moles of A on top divided by total moles. And you could have a mole fraction of B. You'd have moles of B divided by total moles. Mole fraction of C would be moles of C divided by total moles on the bottom, and moles of what you're looking at on the top. The other new concentration unit we're going to look at is called molality. And molality sounds a lot like molarity, but molarity has an R and molality doesn't have an R, it's just L's. Molality gets the symbol little m, and please, from here on in, you must use little m for molality, and you must use big M, capital M, for molarity. Molality is defined as the moles of solute over the kilograms of solvent, and that's kind of interesting, moles of solute over kilograms of solvent. Molarity is moles of solute over liters of solution. So 2 differences between molality and molarity. The top part of both of them is actually the same, but in the denominator, the bottom, molality has the kilograms of solvent, the mass, if you will, of a solvent. Molarity has liters of solution, the volume of solution instead of the mass of the solvent. The third concentration unit is called a weight percent, and weight percent is grams of what you're looking at divided by total grams times 100%. Weight percent is usually a percentage, all right? Mole fraction occasionally is a mole fraction percent, but that's rare, so most of the time it's not. Weight percent, you'll actually will multiply by 100%. And we're going to talk about how to calculate all 3 of these concentration units from particular data. Let's say that we're going to dissolve 1 mole, which is 60 grams of urea. Urea is a solute, and we're dissolving it in 15 moles, which is 270 grams of water. And the question is, what is the mole fraction of urea? Okay, so this is the kind of problem you might see. And the mole fraction of urea would be moles of urea on top divided by total moles. So urea, we have 1 mole of it. We're going to divide it by total moles. So that would be 1 mole of urea plus 15 moles of water. So mathematically, it would be like 1 divided by 16, and that answer comes out to be 0.063. Mole fractions are always numbers no bigger than 1. If it's equal to 1, then you have just that compound, but more often than not, you'd have a number less than 1 but greater than 0. So the mole fraction of urea, 0.063. And again, we got that from moles of urea divided by total moles. Bam. So let's do an example which goes through more details like the one we just saw. All right, and this is an example we're going to go through a lot here. We're going to dissolve 62.1 grams, which is 1.00 moles of ethylene glycol in 250 grams of water. We can use this information to calculate mole fraction, molality, and weight percent of the ethylene glycol. Ethylene glycol is a diol. The picture of it is right there. There are 2 carbons. There's an OH off each carbon, and the other places are just saturated with hydrogens. But that's not really important right now. We're going to use this information to calculate mole fraction, molality, and weight percent. And when you're doing a problem like this, you need to have grams and moles of solute and solvent. So you can see right away you have grams of solute, that's the ethylene glycol, 62.1. You have moles of solute, 1.00 grams. The molar mass of ethylene glycol is 62.1 grams per mole. You also have 250 grams of water, that's the grams of the solvent. We will need the moles of solvent, moles of water too. So one of the things we're going to have to do is turn 250 grams of water into moles. Let's see how this all works out. First thing we're going to do, turn the grams of solvent into moles of solvent. 250 grams of water divided by 18.02 grams per mole, the molar mass of water. We're going to get the moles of water, which is about 13.9 moles. 3 sig figs in, 3 sig figs out, all that kind of stuff. Now we should have all the pieces we need to find mole fraction, which, by the way, mole fraction gets that little chi, that little X symbol right there. Molality, which is the little m, as well as weight percent or mass percent of the ethylene glycol. So mole fraction of ethylene glycol will be moles of ethylene glycol divided by total moles. And total moles here comes from ethylene glycol and water. So mathematically, you would have 1 on the top divide by 1 plus 13.9. Make sure you put those moles in parentheses. Do not put in your calculator 1 divided by 1 plus 13.9. It'll come out to be 14.9, and that's not the right answer. You want to make sure that the whole denominator is placed in parentheses, or just have 13.9 plus 1, something like that. But make sure you do your math right. In the denominator, make sure that's all in parentheses. Anyway, if you've done it right, mole fraction of ethylene glycol, 0.0672. Woohoo, I know, exciting. Anyway, you can calculate the mole fraction of the second component pretty easy. If you only have 2 components, then the mole fractions of both of them together equal 1. So if you needed to find the mole fraction of the water, you could go 1 minus the mole fraction of ethylene glycol, 0.9328 would be the mole fraction of water. And it didn't really ask for it, but that will be pretty helpful in stuff coming up. Molality is moles of solute over kilograms of solvent. Now, we had 250 grams of water, and there are 1,000 grams in a kilogram. So 250 divided by 1,000 is 0.250 kilograms. So molality, 1.00 divided by 0.250, molality 4.00 molal. That's the molality of the ethylene glycol solution, moles over kilograms. And then finally, the last one we haven't done is the mass percent. That's just equal to grams of the ethylene glycol divided by total grams. So in this problem, 62.1 is the mass of the ethylene glycol. We'll divide it by 62.1 plus 250, ethylene glycol plus the water. And again, like on the last problem, make sure that you put this part in parentheses. Make sure that you have them both that way. You want them both in the denominator. Anyway, if you've done it right, it comes out to be 19.9%. So this solution is 19.9% ethylene glycol. And you probably imagined percent water would be 100% minus the ethylene glycol because there's only 2 pieces to it. Percent water, 80.1%. The concentration units handout will have more information on this, and I do encourage you to check it out. There's also some useful guides to help you with these kind of problems in the companion. So here's a problem you might see. Let's say you dissolve 92.0 grams of ethanol in 270 grams of water. And it says, what's the mass percent ethanol in the solution? Okay, so mass percent, aka weight percent, grams of what you're looking at, which is ethanol, divided by total mass. So in this kind of problem, you'd have 92.0 on the top. You would divide by 92.0 plus 270, so mix them both together, multiplied by 100%. If you do that, it comes out to be 25.4% ethanol. So this solution, 25.4%, good to go. If you have molality, you can turn it into mole fraction, and mole fraction you can turn into weight percent, and weight percent you can turn into molality. All three of those are pretty interchangeable. But remember, in the big world of chemistry, molarity is still the important part. All right, molarity is the one that dominates all solutions big time. So we would be remiss in this kind of discussion if we didn't talk about ways to go from molality, mole fraction, and or weight percent to molarity and back and forth. And you can absolutely do this, but you have to remember that molarity is moles of solute per liter of solution. Liter is a volume, and all the other ones have grams, kilograms, moles. And if you want to go from mass and grams to volume, you need a density. So you're going to need the solution density to convert molarity to one of the other three new types of units. Same thing if you want to go from one of the other three types of units to molarity, you're going to need solution density. Now remember that solution density equals solute plus solvent, and all of these things will help us as we go through. So let's look at an example where we want to take a 10.7 molal aqueous sodium hydroxide solution. Let's stop right there for a second. Aqueous means the solvent is water. All right, aqueous is dissolved in water. And sodium hydroxide is going to be the solute. And the solution will be NaOH plus water. Okay, so back to your problem. Convert a 10.7 molal aqueous sodium hydroxide solution to mole fraction, weight percent, and molarity, big M, if the solution density is 1.33 grams per centimeter cubed. No problem. So what we're going to do in this problem is let's first convert the 10.7 molal number to mole fraction and weight percent, because honestly, those are a little bit easier to do. And once we have those down, then we'll go back and we'll turn that kind of information into molarity using the solution density. We won't need the solution density until we hit the molarity. The other ones here are pretty chill. When you're doing these kind of problems, there's always an assumption to start with. And if you're starting with molality, you want to assume you have 1 kilogram of solvent. And if you have a kilogram of solvent and the solution is 10.7 molal, that means you have 10.7 moles of solute. And remember, in this problem, the solvent is water and the solute is NaOH. If you have moles and grams of both solute and solvent, you can knock all of the first three right out. So let's figure that out. A kilogram of water is 1,000 grams. And if you take that 1,000 grams and divide by 18.02 grams per mole, you get 55.5 moles of water. So there we've got mass of water and moles of water. We have 10.7 moles of solute, NaOH. We can turn that into grams using the molar mass. So if you add up an Na, an O, and an H from the periodic table, it's about 40.0 grams per mole. That means 428 grams of solute, NaOH. So now you can see we have moles of solute, moles of NaOH. There it is. We have mass grams of solute. We have moles of solvent, which is this number right here. And we also have grams of water. Wow, this thing is not working very well for me, but you get the idea. All right. You've got all the pieces there. Now we can start putting them together into the first units. Mole fraction is moles of what you're looking at divided by total moles. So mole fraction sodium hydroxide, 10.7 moles NaOH divided by total moles, 10.7 moles of NaOH plus 55.5 moles of water, mole fraction 0.162. The mass percent or weight percent sodium hydroxide would be grams of NaOH divided by total grams times 100%. So there's 428 grams NaOH. We'll divide that by the 1,000 grams of water plus the 428 grams of NaOH, like total mass on the bottom, just NaOH on the top, times 100%. Mass percent, weight percent, 30.0% NaOH. So here we've got mole fraction and weight percent already. We didn't need to use the solution density at all so far. And notice how to solve these, we needed grams and moles of both solute and solvent. And that's how you can conquer those problems, no problem. We still need to conquer molarity. And remember, molarity is moles of solute over liters of solution. The good news here is that we actually already have moles of solute. The 10.7 moles of NaOH, which came from 1 kilogram total of solvent, the 10.7 is the moles of solute. That's the number we're going to use for molarity. But we also need liters of solution. So what people usually do is they take the grams of solute and solvent and add them together, and that's 1428. So in this solution, which is NaOH plus water, we have a total mass of 1428 grams, 1,428 grams. And this number now is what we can use with the density, the 1.33 number up here on the top. So if we take that 14.8 and you divide by the density, 1.33, you're going to get a number which is the centimeters cubed or milliliters. Remember, centimeter cubed and a milliliter are the same. That's the volume of the solution. That's 1,070 milliliters. And if you convert that to liters, 1,000 milliliters per liter, that would be 1.07 liters. So I want to backtrack and highlight that a little bit. You want to add solute plus solvent grams, 1,000 plus 428 in this case. That gives you the total mass of the solution. So 1428, that's all the grams we have. That's the number you can use the density with. So 1428 grams divided by the density of the solution, 1.33. That's how we got the volume of solution. And 1.07 liters is what we want to use in molarity. So molarity, 10.7 moles divided by 1.07 liters of solution. Molarity, 10.0 molar. All right? That's kind of cool. Now, one little thing I can use to help you out here, molarity is almost always a smaller number than the corresponding molality. So in this problem, 10.7 molal was the molality of the solution, and we just calculated that the molarity, 10.0 molar. So molarity is smaller than molality, and most of the time, that's the case. Sometimes in really dilute solutions, they'll be about the same, but that's pretty rare for us. So just most of the time, molarity is a number smaller than molality, and that's a nice way to check yourself. Another unit, which is worth mentioning, although we won't do as much here, is called a parts per million. And a parts per million, ppm, is a very small concentration unit. And it's used a lot by environmental scientists, biologists use it sometimes, geologists, stuff like that. A part per million, 1 part per million, means, in all practical purposes, that you have 1 gram of a substance, the substance you're looking at, in a sample with a total mass of 1 million grams. And 1 million, by the way, is 10 to the 6. So that's 1 gram in 1 million grams. That's a pretty small amount. All right. Now, the density of water is about 1 gram per milliliter, like we've talked about. So if you have 1 million grams, that's pretty close to 1 million milliliters of water. So a lot of times people will make these kind of assumptions to make sense of what parts per million is actually about. There's nothing that says you have to have a parts per million, too. You can also have a parts per thousand, which would be 1 gram of substance in 1,000 grams of the bulk. You could also have a part per billion, which would be 1 gram of the substance in a billion, or 10 to the 9th grams of substance. This parts per thousand is different than the parts per thousand we use in lab. In lab, we use parts per thousand as a measure of precision, how close your measurements are, and the smaller parts per thousand means that your measurements are greater. This parts per thousand is more like a molarity, or a molality for that matter. It represents how much of a type of a solute is in the whole solution or solvent. Kind of cool.
The vapor pressure of a liquid depends on the ability of the liquid's molecules to break intermolecular forces and escape into the vapor phase. A molecule can escape only when it has enough energy and is at the surface of the liquid. When a non-volatile solute is added to a liquid, some of its molecules occupy surface sites in the liquid, displacing volatile solvent molecules. Because fewer solvent molecules get to the surface, fewer can escape, and the vapor pressure of the solution decreases.
Colligative properties are the properties that solutions will exhibit, and it includes things like vapor pressure going down, it includes the boiling points increasing, melting points decreasing, osmosis. And to understand them, we're going to first of all need our new concentration units, and that's cool. But we also need to talk about a little bit more about what's happening in the liquid-vapor equilibrium. And in the last chapter, we looked at how liquids always have a little bit of gas over them, which is the vapor pressure, and vapor pressure changes can be used to describe the difference in boiling point. So if you change the external pressure, you change the boiling point of the liquid, blah, blah, blah. And no big deal. Now, both of these flasks are closed flasks. So the liquid and the gas above it, the vapor pressure, they get in equilibrium pretty fast. If you put a solute in with the solvent, and these solutes, by the way, are non-volatile, which means they don't easily turn into a gas, by the way. But anyway, the solute molecules act as like blockers. And I always use the idea like at a nightclub, they'll have like pretty tough looking people outside the door, and only some people can get in. But if you really, really want to get in, you can probably go through the side door or something like that. So solute acts kind of like a bouncer at a nightclub, all right? And they're keeping the liquid molecules from going into the gas phase, all right? They're blocking the equilibrium. Now, once they get in the gas phase, it's easy to go back to the liquid phase. The blockers don't have anything to do with that. But those solute molecules are keeping the liquid molecules from getting into the gas phase. And we're going to use this idea to better understand where the colligative properties come from. But you can see probably even right now that if the bouncer solute molecules are keeping liquid from going into the gas phase, then your vapor pressure will be lower in a solution than it will be for the pure solvent. Hint, hint for something coming up. This was studied for quite a while, and a guy named Raoult, and I hope I'm saying his name right, I probably am not, but anyway, he came around and realized that, interesting, the mole fraction of the solvent is actually proportional to the vapor pressure of the solvent. Now let's talk about that a little bit. Most of the time in these problems, water will be the solvent. Not always, but a lot of times. As the mole fraction of the solvent goes up, the vapor pressure of the solvent over the solution goes up as well. And what he did then was he came up with this expression right here. And people refer to it as Raoult's law. And it basically says that you have some vapor pressure of pure solvent. And the little zero right there means vapor pressure of pure solvent. So there's actually tables that you can look up, and I'll show you some of these here in a little bit, that are actually vapor pressure values of solvent at different temperatures. And if you're making a solution, then you have to start thinking about mole fraction of solvent. In a pure solvent, the mole fraction would equal 1, no big deal. But in a solution, that mole fraction will be a number number less than 1. So the vapor pressure of the solvent in the solution is this thing right here. And the vapor pressure of the solvent in the solution will be less than the vapor pressure of the pure solvent, P0. And all this is saying basically is that in a solution, your vapor pressure is going to be less, which is what I was babbling about in the last slide. So Raoult's law, which is sometimes referred to as vapor pressure depression, which means the vapor pressure is lowered. The vapor pressure is lowered in a solution relative to the pure solvent. And you can calculate how much lower it is if you know what the vapor pressure of the pure solvent is and you know the mole fraction of the solvent in the solution. Let's do an example of how this works out. Earlier, we did a problem where we had 62.1 grams of ethylene glycol and 250 grams of water. And when we went through the problem, we calculated that the mole fraction of the ethylene glycol was 0.0672. Well, we can use all this information to calculate the vapor pressure of water in the solution at 30 degrees Celsius. So we have here a solution. It's ethylene glycol plus water. And we're going to need the vapor pressure of the pure water. And this number right here, which is 31.8 millimeters of mercury, that's the vapor pressure of pure water at 30 degrees Celsius. So if you have pure water and you heat it to 30 degrees Celsius, the vapor pressure is 31.8. However, in the solution now, the ethylene glycol is going to be our bouncer, our blockers, all right? And they're going to keep the water from going into the gas phase. So the final answer here is going to be a number less than 31.8. And how you calculate it is that first you need the mole fraction of the solvent. And this part is a little weird because most of the time we're interested in the solute, but this is actually one time you need the mole fraction of the solvent. We saw earlier mole fraction of ethylene glycol, 0.0672. There's only two components, ethylene glycol plus water. So together the mole fractions always equal 1. So 1 minus 0.0672 equals the 0.9328, which we might have talked about before, but it's important to highlight again. That's the mole fraction of the solvent in the solution, and that's important. We're going to take that number and multiply it by 31.8, and the answer that you get, 29.7, that's a smaller number than 31.8. So what's this is saying here is that in the ethylene glycol solution, the water's vapor pressure is only 29.7. It was 31.8 millimeters of mercury in pure water, but because solute's there, the ethylene glycol, it's blocking the water from getting into the gas phase. So the vapor pressure has gone down in the presence of ethylene glycol. Vapor pressure depression, the idea behind it, that the vapor pressure goes down, we're going to use that in the other colligative properties. Raoult's law has some kind of cool uses for it sometimes. Mathematically, it's pretty easy to do, but you have to remember to use mole fraction of solvent, and you have to remember that you will need the vapor pressure of the pure solvent at that temperature. So here's a question you might see that's related to Raoult's law. We have 0.0400 moles of iodine, 10.1 grams, in 1.96 moles of carbon tetrachloride, 300 grams. CCl4 is very nonpolar. Iodine is nonpolar, so they make a good solution because their intermolecular forces are close to each other. So given the fact that the vapor pressure of pure CCl4 is 504 millimeters of mercury at this temperature, 65 degrees Celsius, what's the vapor pressure of the CCl4 over this solution? Okay, so in this kind of problem, we're going to use Raoult's law, and we're going to calculate the vapor pressure of the solvent in the solution. And that's going to equal the mole fraction of the solvent, and that's important, times the vapor pressure of the pure solvent at that temperature. And if you read through that data, 504 millimeters of mercury, that's the vapor pressure of pure CCl4 at that temperature. That also means that the answer we're going to calculate here, the vapor pressure of the CCl4 in the solution, the answer will be less than 504. Raoult's law is always about vapor pressure being lowered. You'll never have a vapor pressure equal to or greater than, and that's going to be pretty important, as we're going to see. So in this problem, what we need to do is we need to first of all find the mole fraction of solvent, and that's mole fraction of CCl4. So we'll take the moles of CCl4, 1.96, and divide by the total moles. So we'll divide 1.96 by, parentheses, 0.0400 plus 1.96. That's going to give us the mole fraction of the solvent. And we'll multiply that number by 504 to get the answer. And again, right away, it's not going to be the same as 504 because the vapor pressure is going to go down. It's also not going to be equal to or greater than 504 because the number is going to go down, not go up. I would suspect it's going to be 494. Usually the vapor pressure doesn't make it go down that much, and I kind of think that might be the case. But let's do the math, all right? And what do you know? Instructor knows everything in it. Yeah, I just wrote this problem, okay, so I knew it. But anyway, I digress. First thing to do, find the mole fraction of the solvent, and that's this 0.980 number right there. We're going to multiply that by the vapor pressure of the pure solvent, which is 504. The answer will be less than the vapor pressure of the pure stuff. 494 millimeters of mercury looks great. Raoult's law in the previous example had what's referred to as a non-volatile solute. So what that means, like in the last example there with iodine doesn't have an appreciable vapor pressure. It's a big molar mass compound, and usually big molar mass compounds don't have vapor pressure. However, sometimes both solute and solvent will be volatile, and it's important to talk about how you make this work. So if you have a volatile solute and a volatile solvent, which means they're easy to get into the gas phase, you need to use a slight different version of Raoult's law, and that's right there. And in that example then, the mole fraction is going to be equal to the mole fraction of the first component times the vapor pressure when it's pure first component, plus mole fraction of the second component B times the vapor pressure of pure B. And if you have three components, you can add another one, etc., etc. Let's look at an example. Heptane and octane are both essentially fuels. And octane, which is essentially gasoline, is a liquid. Heptane is also a liquid. So those are the values, the P0 values, those are the vapor pressures for the pure solvent, for pure heptane and for pure octane. And let's say that we mix heptane and octane together such that the mole fraction of the heptane is 0.15. We can use this information to calculate the total vapor pressure of the system. So mole fraction of heptane would be like X size A, the mole fraction, and we would multiply it by the vapor pressure of pure heptane. That would be like 31 torr, all right? Then mole fraction of octane, the other piece, well, if there's only two components, then one minus the first gives you the second. So 0.85 we're going to see is the mole fraction of the octane, and we'll multiply that by the vapor pressure of pure octane, which was the 11 torr number. We're going to add all these pieces together, and then we'll see what's all going down. In this problem, what you want to do is, first of all, this is a two-component system, and if you add the two components together, the mole fraction is always equal to 1. So if the mole fraction of heptane is 0.15, octane will be 1 minus 0.15, or 0.85, and that's kind of cool. Then we're going to use this expanded, if you will, version of Raoult's law, where we have both heptane and octane components. Mole fraction of heptane times the vapor pressure of pure heptane plus mole fraction of octane times vapor pressure of pure octane. And we'll add all this stuff together. So this is kind of a plug and chug problem. 0.15 times 31 plus 0.85 times 11. Make sure the vapor pressures are in the same kind of units. This comes out to be 14.1 torr. So this solution of octane and heptane should have a total vapor pressure 14.1 torr.